Hello Theory 4 students. This lecture is for Wednesday, April 15th, 2020. I believe those of you in this class were all caught up. I received your last assignment and I have it graded and I sent it back to you through Canvas. So we are ready to move on to the next topic in atonal theory. And that topic that I'm going to discuss today is set class and prime form. You may remember that last class we talked about inversion, we talked about transposition of pitch class sets, we talked about transpositional equivalence, and we talked about inversional equivalence. Well, building off of those concepts, we're going to see how sets that are transpositionally equivalent and inversionally equivalent belong to the same family, so to speak. They are very closely related, and that is going to give us some more power, I guess, when it comes to analyzing atonal music. So we'll go ahead and start with set class first, and then I'll get into explaining to you how to find the prime form of any pitch class set. So let's start by defining the term set class. A set class is a family of pitch classes, I should say a family of pitch class sets that are related by transposition and inversion. Okay? So we'll write that down just for an official definition. A family of pitch class, which I'll abbreviate PC, pitch class sets related by transposition and inversion. And from the last lecture, you may remember that the official symbol for transposition is capital T with the subscript N, and the official symbol for inversion is the symbol capital T with a subscript N and then an I, or TNI. So a set class is a family of pitch class sets related by transposition and inversion. Now, normally in any set class, there are usually 24 sets that belong to a single set class. And those 24 sets come from 12 transpositions of any pitch class set are possible, and then an inversion of a pitch class set and its 12 transpositions are also possible. So there are 12 transpositions, and then there are basically 12 inversions. That is to say, there's one inversion, but that can be transposed to 11, start on 11 different pitches as well. So 12 and 12 equals 24. One way perhaps to look at a set class and see why there are normally 24 pitch class sets within a single set class. We could use, for example, the pitch class set that I've been using an example for several lectures now, and that is the pitch class set G, G sharp, B, or you could say the pitch class set 7, 8, and 11. And from the many times that we have used this set over the past several lectures, I know that the normal order of G, G sharp, B, or 7, 8, 11 is the order 7, 8, 11, and that's why I've placed this set in square brackets. So on one side of a set class, we have the normal order of the set, and we have 11 more transpositions. And I'm not going to list them all here. We will take a look at a table in the book in a few minutes, so you can see how this actually works out concretely. But if we have the normal order of a set plus 11 more transpositions so that the set starts on a different pitch class each time, that would be a total of 12 transpositions. Then, if we were to invert the set, that is, subtract all of these pitch class members of the set from 12, I would get 12 minus 7 is 5, 12 minus 8 is 4, and 12 minus 11 is 1. I would get 5, 4, 1. Now, I've done some of the legwork already in preparation for this lecture, and we know that normally when you invert a set, it knocks it out of normal order, which is why I have listed it over here in curvy parentheses rather than square brackets. But as I said, I did a little bit of legwork in preparation for this lecture, and I know that the normal order of 5, 4, 1 happens to be the reverse of that, which is 1, 4, 5. So I can say that the normal order of the inversion of this set is indeed 1, 4, 5. So if this is the inversion of this set, 11 transpositions of this inversion right here are also possible, so that this inversion will start on a different pitch class each time. And so 11 transpositions of one plus the one inversion equals another group of 12 pitch class sets. So a total of 12 pitch class sets on this side, which is just straight transposition, and a total of 12 pitch class sets on this side, which contains all 12 transpositions of the inversion of the set that we started with, gives me a total of 24 pitch class sets that belong to this one large grouping called a set class. Now, on the top of page 513 in your textbook, let's look at a much more concrete example of the same pitch class set, but its complete listing of all the transpositions and inversions for the set class. Right now, we don't necessarily need to know what these numbers mean at the top of the table, of the title of the table, but I do want to show you again that the normal form of the set class with G, G sharp, and B in it is 7, 8, 11. And that's without any transposition. It just is what it is. 7, 8, 11. Then if we transpose this set class up by a half step 11 more times, we're going to have this pitch class set start on a different integer or pitch class every successive time until all of the transpositions are exhausted. Remember, there are a total of 12 pitch classes in atone music. So if we have each of these PC sets starting with a different pitch class set, and that encompasses all 12 of them, we have all the possible transpositions of our original pitch class set, 7, 8, 11. So that's what's on the left side of the table here of the set class. We also figured out on a previous screen that the normal order of the inversion of pitch class set 7, 8, 11 is 1, 4, 5. So here's the normal order of that inversion with no transposition involved. And then again, there are 11 transpositions of this pitch class set for a total of 12 inversions. So 12 transpositions on this side, and the inversion plus its 11 transpositions on this side equals 12, and 12 plus 12 is 24. So again, generally, the point is there are usually, I should say, 24 pitch class sets belonging to one single set class, which is again a family of these transpositionally and inversionally related pitch class sets. Now, with so many pitch class sets in a set class, wouldn't it be nice if there was a label that we could find that would generically represent all of the transpositions and all of the inversions in this set class, so that we could get one name or one label to refer to and represent all of these 24 pitch class sets? That would be really nice, because it would reduce the amount of pitch class sets we have to deal with, and it would give me one single unified label for the set class that represents all these related transpositions and inversions. Well, the good news is there is a way to come up with a label to name and represent the set class, which includes all of these pitch class sets. And the name for a pitch class set, and the way we label a pitch class, or a set class, I should say, the name for a set class is called a prime form. Prime form. So if we can find prime form based on these 24 pitch class sets, if we can boil them down to just one set with a label, then what we can do is we can start comparing pitch class sets in atonal pieces of music much more quickly and much more efficiently. We don't have to worry about the inversions that are possible of a pitch class set in the music. We don't have to worry about the transpositions. We can boil them all down to just one label, one pitch class set, and that will represent all the transpositions and all the inversions, and really speed up the process of analyzing atonal music. So again, the term prime form is basically what that is it's the label or the name of the set class. It's the name that represents the entire family of related transpositions and inversions within a set class. Now, a set in prime form always begins with a 0. Always begins with a 0. And in this case, the 0 does not necessarily represent the pitch class C per se, because when we find the prime form or the name of a set class, we're going into much broader or generic terms. We're not specifically talking about a specific pitch class set with specific pitch class integers. We're just finding the name for the entire set class that is a generic representation for all the transpositions and inversions. So the fact that a prime form will always start with 0 does not necessarily mean that that 0 represents C. It could really represent any pitch class, C of which could be one of them. But for what we need to know that a prime form always begins, a set in prime form always begins with 0. Okay? Now, to determine the prime form of a set, the book has it's a 4-step process as listed, although it includes a few more steps kind of underlying in there to find the prime form of any set. What I have done is I have kind of curtailed it and shortened it and boiled it down to exactly 4 steps. And I think I'd like to use the steps that I have chosen here. Both ways will find the prime form of any set. But the steps that I have kind of eliminate some of the busy work that the book has you do. So anyways, let's just go look at those 4 steps to figure out how to find the prime form or the name of any pitch class, set class. I will be providing you this list of steps to find the prime form of a pitch class set through Canvas. I'll be sending that to you as a PDF file, and so that you can have this, you can print it out, you can refer to it whenever you want. Okay. Let me go through the 4 steps, read through them here in case you can't see them, and then we'll go through some examples of some actual pitch class sets that we will be translating or transforming into or turning into finding the prime form of. So here we have number 1, the first step for determine the prime form of any pitch class set is to first of all determine the normal order of that pitch class set. After you find the normal order, number 2, we're going to reduce the first integer of that set to 0 by subtracting the first integer from itself, and then subtracting the same integer from all the other members of the set as well. That'll bring the first member of the set, or the first integer, down to 0, and it'll reduce all the other members of the set by the same amount. So it's just basically like a transposition of our original normal order. Step number 3 says, invert the set obtained in step 2 by subtracting each member of the set from the last number of the set, and rewrite these new integers in ascending order. Hopefully that will make a little more sense as I go through a few examples in a minute. And then finally, step 4 says to add the integers of the pitch class sets obtained in step 2 and step 3. Whichever set yields the smallest sum, that is the ultimate prime form of the set. Okay. So again, if you need to refer to this, these steps before I actually send you the PDF file, you're welcome to pause your video, go back, relook at that. If you want to even write this list down, you're welcome to, but I will be sending a document to you through Canvas with these steps. Alright, let's go ahead and start from scratch with an unordered pitch class set. And again, we'll use the same one that I've been using as an example for several lectures. We'll just go through the process with this one. For example, in the unordered set 11, 8, 7, we know that those pitch class integers represent the notes of B and G sharp and G. And from the beginning of this lecture and from previous lectures, we also know that the best or the smallest or most compact order of these 3 pitches is the order G first, then G sharp, and then B. Every other order that I were to get, if I were to start with G sharp for instance, and then the pitches all have to be in ascending order within an octave, G sharp, B, and G natural. This outside interval is very large. It's actually 11 half steps, whereas this outside interval is only 4 half steps, a major third, G to B. And the only other order possible is if we start on a B, and then we would have a G natural followed by a G sharp, and we know that this outside interval from B to G sharp happens to be a major sixth, which happens to be 9 half steps. 9 half steps. So the normal order for this pitch class set is indeed G, G sharp, B. Because it spans the smallest outside interval, and therefore the normal order of this unordered set here is 7 for G, 8 for G sharp, and 11 for B. Okay. That's step one of finding the prime form of a pitch class set. Here is the normal order. Okay. Now, step two tells us to reduce this normal order set we just found, to reduce it so that the first integer of the set is 0. We have to get this set, transpose the set in such a way so that we get the first number of the set to be 0. Okay? Now, what you can do is you can add 5 to all of these members of the set, and when you do, you'll get 7 plus 5 is 12, and in mod 12, that is 0. 8 plus 5 is 13, and in mod 12, that becomes 1. And 11 plus 5 is 16, and again, mod 12, that becomes 4. So we're just transposing the normal order set of step 1 until we get to an array, until the first number of the set is a 0. That's what we're trying to get to. We transpose all the other members of the set by the same amount, so their numbers will change as well. Now, in my step 2, what I have you do, instead of finding a number to add to all the members of this set so that the first number is 0, what I do is I say, well, just subtract all of the members of, subtract 7 from all of the members of the set, right? I take the first integer 7, and if I subtract 7 from every member of the set, 7 minus 7 is 0, 8 minus 7 is 1, and 11 minus 7 is 4. I get the same thing. So whichever way you want to do it, in a future example, I'll probably just take the first integer of my normal order and subtract it from all of the members of the set so that I can get a set that starts with 0. And again, whenever you transpose a set that's in normal order, it stays in normal order in the transposition. Okay, so now I have I have a transposition of my normal order which is in normal order, but it starts with 0. So that gets me a lot closer to finding prime form. Okay, we're going to come back to this set in a second. Okay. In the meantime, I need to go on to step 3, and that is, what I need to do is find the inversion of this set, and then I need to put that inversion into normal order, because remember, the inversion of a set in normal order knocks it out of normal order. So find the inversion of this set, put it into normal order, and then find a normal order of that set that starts with 0. Because then I'm comparing apples with apples. Okay. A kind of a shortcut way to do all of these steps in one step, that is step 3. What I'm going to do is, instead of subtracting all of these numbers from 12, which would be normally the way to find an inversion, I'm just going to subtract all of the members of this set from the largest member of the set, that is from 4. Because if I subtract all the members of this set from 4, what I'm going to end up with is a set that contains a 0 in it. And I'll be able to put the 0 then in the front, and that's exactly what I want, again, to find prime form. Okay, so let's do that over here. If I have the set 0, 1, and 4, and I subtract all of these members of this set from 4, so 4 minus 0, 4 minus 1, and 4 minus 4, what I end up getting is the set 4, 3, 0. And again, it's not in normal order. Now, I know this is skirting a little bit of the issue here, but it speeds the process up a lot. And that is, generally when you invert a set in normal order, what happens, not all the time, but usually what happens is that the set is spit out in reverse normal order. Reverse normal order. So, yes, this is not normal order because I've inverted the set. But generally when you invert a set, what happens is you get the set exactly in reverse normal order. Not every time, but I'd say at least 9 times out of 10 this is true. So if I just rearrange this inverted set 430, I just rewrite it in reverse order, that is with the smallest number first and the largest number last, then what I'm going to do is I'm going to get normal order, and that is going to be 0, 3, 4. Just the reverse of this set. Okay? So, as a quick summary here, what I've done is I've taken a pitch class set and I've found its normal order. That's step one. Second step is to get this set to start with a 0. So I subtract all the members of the set. Scratch that. I take the smallest number of the set and I subtract that integer from all the members of the set. And I'm guaranteed then to get a normal order set that starts with 0. That is step 2. Step 3 is to find the normal order, find the inversion of this set, find its normal order, and then reduce that normal order to a set that starts with a 0. Well, again, covering all those steps kind of quickly so that you don't have to do each and every single step. What I do then is I take the set I got from step 2, I subtract all the members of the set from the largest integer of the set, that is in this case 4, so 4 minus 0, 4 minus 1, and 4 minus 4. I get another set which is not in normal order, but it will be 9 times out of 10 in reverse normal order. So once I get that answer, I flip it around, starting with the 0, and I write it as 0, 3, 4. Okay. Now, that gives me the answer to step 3. Now for step 4, the final step to find the prime form of any set, it is to compare these two. The normal order of the transposition side of the set class that starts with a 0, and the normal order of the inversion side of the set class that starts with a 0. Let's compare these two. Which of these two normal orders that I have boxed here is most densely packed to the left of the set? In other words, which of these two has the smallest intervals between the members of the set on the left side rather than on the right side? Well, one way to find that is to actually add the integers of each pitch class set. And when I add 4 plus 1 plus 0, I get a total of 5. And when I add 0 plus 3 plus 4, I get a total of 7. Which normal order yields the smallest sum? The answer is this one. 5 is smaller than 7. And so that means this normal order is most densely packed to the left of the set. And that means this one versus this one, the 0, 1, 4 happens to be our prime form. That is, our ultimate reduced version of all 12 transpositions, all 12 inversions that are related to each other in this set class. This is the most ultimate reduced version, and therefore we are going to name our set class 0, 1, 4. And again, the prime form of a set is the set class's name. So the prime form of my original set here, it happens to be 0, 1, 4. And the way we notate a prime form is just a little different than we notate other set classes. Instead of using square brackets with commas, we're going to use curvy brackets, and we're going to use no commas at all. Okay? So, curvy brackets with commas means an unordered pitch class set. Square brackets with commas in between the members of the set means normal order of a set. But curvy parentheses, I should say, with no commas at all, this gives us the ultimate reduction. We call this prime form. It gives us the name, and prime form is the name of our set class. The name of our set class. So, let me go back to the example that is in your book. And that is, again, on page 513. You can see that the original set I started talking about, and the set that I did just find prime form for, you can see that the name of this set class is there in parentheses. It is 0, 1, 4. You do not necessarily need to know what this 3-3 means. All I can tell you is that this 3-3 is a name that was given to set classes by a guy named Alan Fort, and he actually organized or ordered all of the possible prime forms for any possible pitch class set in atonal music. He organized those according to the number of members in the pitch class set. So there are 3 members in this class, this set class 0, 1, 4, and that's where the first 3 comes from. And the second 3 doesn't really mean a whole lot. It's just the ordering that it is in his list. Boy, this is really hard to explain over the camera, but I hope this is somewhat making sense. I'm definitely going to go through another example so that we can find the prime form of a set. Anyways, 0, 1, 4, again, I should say, is the ultimate, most reduced, most densely packed to the left of a set way that we can label all of the transpositions that are related to each other and all of the inversions that are related to each other. This represents all of them with just one single unified label. So, just as a quick review about what this 0, 1, 4 means. This 0, 1, 4, this label takes into account all of the transpositional and inversionally equivalent sets of set, the one we started with, 7, 8, 11. Okay? It immensely speeds up the set comparison process when analyzing atonal music, because we don't have to be concerned when we analyze atonal music and we take a pitch class set of just 3 pitch classes. We don't have to be concerned about transpositions really or inversions anymore. We've checked out all the possibilities. We've boiled them all down to 1. And so if we boil all the set classes in an atonal piece of music down to 1 label, then we can compare much more quickly, and we don't have to worry about whether or not the sets are transposed or inverted or not. We're working on the same terms, comparing apples with apples. Another way that you could think of the 0, 1, 4, you could say that 0, 1, 4 could appear 24 different ways in a piece of music, but we now have a method for reducing 24 sets to one that is related to them all. Okay? So again, just this one label, 0, 1, 4, represents a conglomerate or a huge collection or group of 24 transpositionally and inversionally related sets. Again, we're boiling it down to just one piece of information, which is much easier to work with than 24 pieces of information. Now, just for your information, because this can be very helpful, especially with the next assignment that I'm going to give you, in the back of your textbook is an appendix. It's called Appendix C, and in that appendix are listed every single possible prime form of every single possible pitch class set that there would be in atonal music. And I'm going to go to that just to show you a little bit about how to read it, and then hopefully you can use that information to check your answers for finding prime form in the future. So this appendix begins on page 559 in the back of your book. And, well, let me go ahead and unfreeze this so that you can see everything there. Yeah, I guess I'm not going to be able to get it any better than this. This is about as good as I'm going to be able to get it. Okay, so basically at the beginning of this appendix, we have a list of trichords. Trichords is a fancy way of saying pitch class sets that contain 3 members. 3 pitch classes. Okay. These are the prime forms of all the pitch classes that have just 3 members to them. Okay. There are 12 possible prime forms. And the prime forms are listed as 012, 013, 014, etc., 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 all the way down. Now, what this means is that whenever you're trying to find the prime form of a pitch class set that has 3 members to it, do the work, do the 4 steps that I just talked about, and then what your final answer is, come to the appendix and check to see if your prime form is listed here in the column of trichords. If you find the prime form that you found, if you find it located in this appendix, that means you did your calculations correctly, because it's listed here in the appendix. It exists. If, after finding your prime form, you do not see your prime form listed in this appendix somewhere, that means you calculated the prime form wrong, and you need to go back and start redoing some of the steps until you find your error. Okay? Over on the left, this column is abbreviated FN, that stands for Fort name. Again, this is just another name that theorist, Alan Fort, gave to all of these prime forms here. He starts with a 3 because there are 3 members in each of these sets, and then he just lists them in order, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can see that they generally do get larger numbers as you go down the column. The prime forms do. Okay? You do not have to worry about what vector is yet. Do not worry about that column, nor do you have to worry about what the DF column means. Maybe I can talk about that a little bit in a later lecture. Okay? But again, this appendix is very important, so please mark the first page of Appendix C in the back of your book, because you can refer to it very frequently to check your answers for prime form. On the top of page 560, still in the appendix, you can see that there are about 29 different prime forms for any pitch class set that has 4 members in it. So if your pitch class set contains 4 pitch classes, or there are 4 integers in your set, then there are possible of 29 prime forms for that set. And again, what you want to do when you're finding the prime form for a pitch class set that contains 4 members, go through the steps we talked about, and then when your final answer, you found it, see if it's listed in this column here on the page 560. If it's not listed here, that means you did your calculations wrong and you have to go find your error. But if you find your set listed here in the prime form column, that means you're okay and you did your calculations correctly. Let's start with an unordered pitch class set again, and let's go through the steps once again for finding the prime form. Let's use this unordered set to begin with 8, 4, 3, and 1. Remember, curly parentheses with commas means the pitch class set is unordered. Nothing has been done to it. It's like we've just taken these pitch classes out of an atonal piece and grouped them together in a random order. Okay. Now, step 1 is to find the normal order of this set. The normal order of this set. And what I'm going to do is I'm going to go to a screen with some staff musical staves in it, and you may want to do this on your own staff paper. Use it as scratch paper to find the normal order of any given set. So I'm going to go with 8, 4, 3, 1. And I'm going to use the shortcut method for finding normal order that I talked about a couple lectures ago. Okay? Let's go ahead and turn these integers, translate them into pitch letter names. Okay? So 8 is going to be G sharp or A flat. 4 is going to be E. 3 is going to be E flat. And 1 is going to be C sharp. So to find the normal order of these, just start with one of them and write the pitches in ascending order within an octave. Okay. So I'm going to start with the A flat. Okay. The next pitch class in this set that would be in ascending order within the span of an octave is going to be the C sharp. Then the next one would be E flat. And the next one would be E natural. Now, rather than writing out the 4 or the 3 other arrangements to find normal order, I'm going to use my shortcut method, which tells me and says that I can rewrite the first pitch of my ordering at the end an octave higher. Okay? Now, what I do is I look at the melodic intervals between each successive pitch class in this set, and I find the largest interval and I bracket it. So, it looks like this interval is kind of big, this interval is kind of big, this one is not, this interval is kind of big. Well, which one is the largest? Well, A flat to C sharp is the same as A flat to D flat, and harmonically, that is a perfect fourth. And that should contain 5 half steps. Okay. C sharp to E flat, that is a diminished third. Diminished third, so that really only contains about 2 half steps. And then the other one that looks kind of big is E natural up to A flat. And harmonically, E natural to G sharp, that is a major third. A major third. And that contains only 4 half steps. So it looks like the largest interval between any 2 adjacent pitches in this set is this interval right here. And let me use a different color maybe so it stands out a little more. A flat to C sharp. I bracketed it. Okay. Rewrite the members of this set now, starting with the higher of the 2 notes of the largest interval, or the second note that is bracketed. The second of those bracketed notes is C sharp. Rewrite those pitches again, starting with this note, and put them in ascending order within an octave. So we have C sharp, then we have E flat, and we have E natural, and then we have A flat. This is indeed the normal order of my original pitch class set. Right here, normal order. And let's turn these pitches into pitch class integers. So that's going to be 1, 3, 4, and 8. There, I've completed step 1 for finding the prime form of a pitch class set. My normal order is 1, 3, 4, 8. Step 2 asks me to reduce this normal order set so that it starts with a 0. And if I subtract the smallest number of this set, which is 1, if I subtract 1 from every member of the set in turn, I'm going to end up with a set that starts with 0, and all the other members of the set are going to be reduced proportionately. So let's subtract 1 from every member of this set. 1 minus 1 is 0, 3 minus 1 is 2, 4 minus 1 is 3, and 8 minus 1 is 7. Okay? So, this is going to be an important set for comparison. This eliminates all of the transpositions on the left side of my set class table. It eliminates all of them except for one that starts with 0. And it's in normal order. 0, 2, 3, 7. Now step 3 for finding prime form asks me to invert this set, find its normal order, and then reduce that set so that it starts with a 0. In order to take care of all those steps, my step 3 just tells us to take this set and subtract the largest member of the set, that is 7, subtracts all the members of this set from 7. Okay, so let's do that over here. So I've got 0, 2, 3, 7. And if I subtract all these members from 7 itself, so 7 minus 0, 7 minus 2, 7 minus 3, and 7 minus 7, what I'm going to get is an unordered set. 7, 7 minus 2 is 5, 7 minus 3 is 4, and 7 minus 7 is 0. I'm going to get 7, 5, 4, 0. Now, again, I can assume for the most part, not every time, but maybe 95% of the time, that this set I've just written after inverting it is in exact reverse normal order. So if I just rewrite the integers here from smallest to largest, or reverse the order, then I should get it in normal order. Alright, so let's go ahead and do that right here. So the normal order of this set is going to be 0, 4, 5, 7. And that is now the normal order of this. So, this takes care of all the transpositions of all the inversions on the right side of the set class table. It reduces it to just one that starts with 0. And now we're ready to complete step 4. Step 4 says compare these two normal orders. And I've got them both circled in blue. Okay. Let's add the integers of each pitch class set together and see what kind of a sum we get. 4 plus 5 plus 7 is, it looks like 16, I think. That's what it adds up to. 2 plus 3 plus 7 added up together equals 12. Which of these normal orders yields the smaller sum? The answer is this one here, 12. So I'm going to say then that my final prime form, the name of my entire set class, of which this original set is part of, the final prime form is 0, 2, 3, 7, and I'm going to list it with curly parentheses and no commas. 0, 2, 3, 7. That is my ultimate answer. And that is the prime form, the name or the label, the set that represents this one and all of the sets that are transpositionally and inversionally equivalent to that one. Alright, I'd like to go through maybe one more example of how to find the prime form of a given set. And hopefully, after this third example, you'll have seen enough and you'll have learned enough from this lecture, or else you can go back, rewind it, and play some of it again, so that where you can find the prime forms of some given sets on your own, which is going to be your homework for well, later in this week or either beginning of next week. Okay, so let's do one more example together. Let's say we want to do, let's start with the, I'm just looking in Appendix C to see if I can find a good one. One that actually comes out with an interesting answer for comparison at the end. Oh, I guess we can do that one. Let's try 4130. Actually, I'm going to change that. Let's transpose it a little bit. How about 5, 2, 4, 1? 5, 2, 4, 1. Okay? To find the prime form, step 1, find the normal order of this set. These pitches are F, D, E, and C sharp. F, D, E, and C sharp. Let me go ahead and write those down so I don't forget. F, D, E, and C sharp. Okay. Let's go ahead and start writing them on the staff in ascending order within an octave. It doesn't matter which one you want to start with. I can actually look at these pitches and I can tell that really the most compact arrangement of these 4 pitches is going to be the arrangement where I start with the C sharp. Let's just check it out and verify that to be true. So if I start with the C sharp, the next pitch in ascending order within an octave will be D, the next one will be E, and the next one will be F. Using my shortcut method for finding normal order, what I would do is I would duplicate the first pitch of this set, write it an octave higher at the end of the set. Looking at this arrangement now, which 2 consecutive pitches give us the largest interval? In other words, the largest interval is between which 2 consecutive pitches? Well, it's actually going to be between these 2 right here. You can see that's the largest interval. So the shortcut method for finding normal order says, well then just rewrite this set starting with the higher of the 2 bracketed pitches. Well, if I do that, I'm going to get the same that I started with. Starting with C sharp is going to prove and verify that this is indeed the normal order of my 4-member set that I started with. Okay. So, this is the normal order. Let's translate these pitches into pitch class integers, and we'll list the normal order in square brackets. The normal order is going to be 1, 2, 4, and 5. Again, that is step 1 for finding the prime form, right? Because that's our ultimate goal, is to find the prime form. Let's make this set, do some little bit of math to translate and to turn this set into a set that starts with 0. That's step 2. The way I do it is I take the smallest integer of the set and subtract that number from all the members of the set. So the smallest number is 1. We subtract 1. We take all of these and subtract 1 from them. What we're going to get is 1 minus 1 is 0, 2 minus 1 is 1, 4 minus 1 is 3, and 5 minus 1 is 4. I hope you can see that if you subtract every member of the set, the smallest number of the set from every member of the set, you'll be guaranteed to get the first number will start with 0, and the rest will be reduced proportionately so that the set still has the same internal intervallic content. Alright, so that's the normal order with 0 as the first digit in the set. And we're going to use that to compare it at the end to find our prime form. Step 3 says to invert this set, put it in normal order, and have it start with 0. Reduce it so that it starts with 0. Okay, so what I'm going to do is now I'm going to take the largest member of the set, that is 4 in this case, and I'm going to subtract all of the members of the set from 4 to invert it so that it still has a 0 in it. Okay, so I'll write that over here. 4, let's just imagine here, 4 minus 0 is 4. 4 minus 1 is 3. 4 minus 3 is 1. And 4 minus 4 is 0. So what I have, since I inverted this, is I have a set in reverse normal order. Putting it in normal order means I just rearrange them so that it starts with the lowest number and goes to the highest number. write it in reverse order, and that gives me the set, which will be in normal order, 0, 1, 3, 4. Okay, now, this is a little different. It looks like the most reduced representation of the transposition side of the set class is 0, 1, 3, 4, that's its normal order. And the most reduced side of the inversion side of the set class, its normal order is also 0, 1, 3, 4. If I were to add the integers of each of these sets together, I would get a sum of 8 for this one and a sum of 8 for this one. They are equivalent. There is no smaller integer to choose which set is the prime form. Well, therefore, the prime form of the set must be 0, 1, 3, 4. There is no other option. And this time I'll write the prime form in green. Curly parentheses with no commas, 0, 1, 3, 4. I'm saying that that is the prime form and the way I can check my answer to see if I've calculated the prime form correctly is to look in the appendix in the back of your book. Let's go there. I think it's going to be around page 560. And let's look to see if 0, 1, 3, 4 shows up somewhere in that list. Sure enough, on page 560, it's the third one down in the prime form column. 0, 1, 3, 4 is there. So that means I have calculated my prime form correctly because it is printed, it exists in Appendix C in the back of your book. By the way, tetrachords, tetra is the prefix meaning 4. So these are all the prime forms of the pitch class sets that exist in atone music with 4 members. Now, I have gone through all of the exercises that you're going to be doing for homework, and I have verified that you should be able to find all of the prime forms for these. I don't think there's anything really super tricky about any of the exercises. The homework that I'm going to assign on Canvas, I'll give you the details, but I'll let you know right here. It is page 300 again in your workbook. I know we have already done part of this page before. We have found the normal orders for all of those 6 sets on that page. But now I want you to go further and I want you to find the prime form for all of the 6 exercises on workbook page 300. Okay. So you'll be doing that, and when you go ahead and find the prime forms and you fill in the answers, when you're done you can go ahead and send that a picture of that document or a scan of that document to me. And again, I'll give you all the details on Canvas for when it's due, that kind of thing. So, I think I'm going to go ahead and stop the lecture here because I probably talked long enough. This is a hard concept, again, to teach and explain, especially over video, but hopefully you'll be able to get the gist of how to find prime form of any set class by rewinding the video and just looking at the examples and listening to the parts that you need to again so that it cements in your mind. So hopefully you'll have a good rest of your week, and I'll see you probably next time for another lecture.